So last time we introduced functional languages, functional programming languages, and the Lisp programming language, schema, which is similar to Lisp. So today we'll go through more examples. Basically here we're trying to understand how this functional programming language differs from the C-like languages that we are used to. Okay, so we will look into more examples. So the first example is writing an is-even function. Now defining functions in schema, you will need to use the define keyword. And the define keyword is also, defining a function is also a list, is also viewed as a list. Everything is a list. Now, what do you think the elements of this function definition, list should be? What should the elements be? So the define keyword is one of them. The other element in the list is the name of the function and the signature of the function. So it's is even. It's let me write it as is even, and the signature of this function is the parameters that it takes, and it only takes one variable or one parameter, which is x. So this is element 1 in the list, element 2 in the list. Element 3 is the actual body of the function. So the actual body of the function will be another element in the list. So here I will put the body of the function. Then don't forget to close. So this is the body. And don't forget to close this definition. So in schema, make sure that you close all the parentheses that you open. So now how does this work? So last time we studied the if. So in C-like languages, we do if x mod or x mod 2 equals 0, return true, else return false. So here, how do we have an if, and the condition is x mod 2 equals 0. But now with the syntax, with the schema syntax, we don't have this same syntax. We have the what? We have equal of mod. So mod x and 2. So x and 2, x mod 2. This should be equal, if this is equal to what? Equal to 0. So this is our condition. So the condition is basically, the idea, it's prefix based. Prefix notation. And prefix notation means the operation comes first, or the operator comes first. So on a high level, we're comparing this with 0, the mod with 0, and the mod itself is operator x and 2. Any questions? So basically think of it as prefix notation. In fact, it's closer to how an abstract syntax tree is constructed in a compiler, and how a compiler generates code, because it will be like equality checking of the mod and 0, and the mod is mod x and 2. So you calculate the mod, then you compare it with, here compare with 0. So if we compare it with 0, this is true. What do? We return true. And true is this. So this is true in schema. And this is false. And there is no return because it's functional programming. So this is like the function evaluates to true. If this condition is true, this is the then. Now we need the else, in fact. So I closed this too early. So this is the if. If the condition is true, we do this. Else we do what? False. And there is no return. Remember, there is no return. It just says, if this condition is true, this evaluates to true. Else, this evaluates to false. Then we close all the parentheses. So we want to make sure that this whole thing is the body of the function. So this is the well, first of all, the condition. This is the then. This is the else. Then what do we need to close? Did we close this? No, we did not close this. Did we close everything? What's that we didn't close?
Before the if.
Before the if?
Yeah, that one needs to be closed.
Okay, so what's this? So this is the yeah. So because this is a member of the list, so this is the body part of the list. So the list, the high-level list, is the keyword define, the signature, and the body. And we didn't close this for the body. In fact, there is a more compact way of writing this, which is we can write this as define is even x. And we don't have to do if and else. Why? Because it's just this equality checking between mod x and 2 returns a Boolean. So this itself is just can be the body of the function. So we can just say this is equal mod x2, and that's it. And we close this and this. Yeah. Sorry. We did not equate it with 0. Yeah, sorry. So it's equal of mod x2 with 0. Okay. So the equality of this and 0 is the body of the function, and this is what it will return. And then we'll need to close this. So this is like saying in C-like languages, it's like saying return x mod 2 equals 0. Right? Can't we say this? Yeah. So we can say it like this. We don't have to do if else. Just the logical value, the Boolean value of the comparison between x mod 2 and 0. Okay. So this is the is even. So let's take more examples. Is it recording? Yeah. Okay, so the next example is sum of the squares. Sum of squares. So it takes two numbers and it sums the squares. So it takes x and y, and it calculates, it returns x squared plus y squared. So the input is x and y, the output is x squared plus y squared, and we define this as again sum of squares, and the parameters are, what are the parameters? X and y. So we close this. This is the signature part of the definition. So we have keyword define, signature, then body of the function. What's the body of the function? Now we do it in prefix notation. What's the first thing that we do? What's the high level operation in prefix notation for this? Yeah, plus. So it's like this is plus the multiplication of x by x and the multiplication of y by y. So high level is plus. Within that there is a multiplication and another multiplication. So we have the plus of x multiplied by itself, and again prefix notation, which is multiply the operation first, multiplication of x and x. Then the other operand for the plus is what? Multiplication of y and y. Now, how many parentheses do we need to close? 2. We need to close this. Now we close the body of the function, and then we close the first parentheses. Okay, so again, this is the keyword. This is the signature, and this is the body, or not including this, but this. This is the body of the function. Keyword, signature, body, and interestingly, this is viewed as a list. So this function definition is viewed as a list, which has 3 elements. Element number 1 is the keyword. Element number 2 is the signature. Element number 3 is the body of the function. So let's take the next example. Let's make it recursive. So what's a classical example on recursion? One of the classical examples on recursion is the factorial. Right? So factorial. So well, let's just use that for the writing things in C. So in C or Java or C-like languages, the factorial function, factorial of x or long, factorial of x. How do we write the factorial? So the factorial is return x times what? X minus 1. Right? Oh, sorry, it's not the factorial of x minus 1. So multiply x by factorial of x minus 1. What's the base case? If x equals 0, then we return. What's factorial of 0? Factorial of 0 is 1. So if x equals 0, return 1. Okay, so this is the factorial in the C-like languages that we are familiar with. Now we will have to translate this into or to rewrite it in schema. Remember that everything is prefix notation. So we have an if, so we can compare. So we have to do define, then factorial. How many parameters does it take? 1, which is x. Now the body of the function. The first thing is we compare x with 0. So how do we compare this in the schema syntax? How do we compare x with 0? The comparison comes first. So if equality of x and 0, if equality applied to x and 0, what do we do? Return 1. Do we have a return keyword? No, it's just 1. So the function evaluates to 1. So if it's 0, the function evaluates to 1. Else what? We return the multiplication of x and factorial of x minus 1. So what should we put first here? Multiplication, the operation first. Prefix notation, remember the operation comes first. The multiplication of x and factorial. So do we do this, x minus 1? No. It doesn't have, this syntax of function and this argument between parentheses. No. X minus 1. Yeah, exactly. So the factorial minus x and 1. So operation comes first. Minus x and 1. Now what do I need? Does this look okay? What do I need?
You need parentheses.
Yeah, parentheses so that it knows that this is one piece. This whole thing is one piece. Right? Now what do I need to close? Yeah, exactly. So the if parentheses
And the else parentheses.
Yeah, so okay. So first of all, so this is the else part. And then the if, and then the define. Okay. Yeah, I need more parentheses. Why? Because this will not recognize the factorial and this as one piece. I need to define the factorial for this multiplication. The second operand for the multiplication is not fact. It's fact and this. So I still need parentheses here for this so that it takes factorial of this as one piece and multiply it by x. So, okay.
The one can just be left off without like any broken parentheses, just
Which one?
after the if, on the end of the if line, the one just came by itself without any parentheses.
No, because we're not done yet. So the if consists of if. This is the condition for the if. This is condition. This is the then clause. And all of this is the else clause. So the if is a list that consists of 4 elements. Element number 1 is the if keyword. Element number 2 is the condition. Element number 3 is the then. Element number 4 is the else. Okay? Yeah, so we'll, we're not used to this. Yeah, so anything like this, in order to get used to it, you need to practice clearly, and then you will get used to this. We are used to this. I mean, I can write this in less than a minute, but when I write this, I will have to think, to do a lot of thinking, because it's a syntax that I'm not used to, and even it's a way of thinking that I'm not used to. Okay, so this is the factorial. So now the fun part is list processing operations in schema and Lisp. So we have these operations, these built-in operations on lists, which are the car operation, the cadr operation, or the CDR, and the cons. So these three operations, these are the three basic list operations. So this just means get the head of the list. Now this get the rest, not the tail, but the rest of the list. The rest of the list is everything but the head. And this, given a head and a rest, build a list. So cons for construct. So now let's look into examples. Okay, so what will this return? Car is just the head. So the head of this list is 7. So this will return 7. So if you type this, you will get 7. This is the output. You will get 7. Now what if you do CDR of 7, 3, 5? What will this return? Yeah, 3, 5, the rest. But 3, 5 as a list. Yeah, in fact, we need to define these as data. Okay. Now, what about this? 3, 4, 5, 9. Or if we define this as a list, and 6, 5. Oh. Okay, I need one more. Now, what's the head of this list? Yeah, 3, 4. So it's a list of lists. It's a list of lists. So this is the head. And this is the rest. So the head is going to be 3, 4. So on the top level here, this is a list of 3 elements. This is the head and this is the rest. Okay, now what's the CDR of the same list? It will return the rest, which is 5, 9, 5, 9, 6, 5, 5, 9, 6, 5 as a list. So remember, the head is just one element. CDR is going to return a list. So this returns an element this returns a list. Okay, so now what if let's take some examples on construct. So construct 7 and 9, 2. Construct 7 and 9, 2. The output of this is going to be, it's going to build a list that consists of this element added to these two elements. So it's going to give you 7, 9, 2, 7, 9, 2 as a list. Okay, so it's going to give you 7, 9, 2 as a list. So it will add the head to this, and it will give you 7. Why did I put these on? 7, 9, 2.
Question?
Yeah.
What is the point of the colon, or no, not colon, the parentheses? That's not the word for either. Right before the 9, 2, before the apostrophe, that's the word.
Okay.
The point of the apostrophe?
Yeah, the single quote. Yeah. So so it means do not execute this. Treat this as a data list, a list of data. It's not an executable list. So we said in lecture 1, that's what we use for a data list. Otherwise, schema will try to execute it. An executable list is a list that starts with an operation. Any list that doesn't start with an operation is not an executable list. It's a data list, and that's why. And you need to indicate this by saying this is data. This is not an executable list. Now, what if we have something like this? So here the result is kind of surprising. Cons, let's say 9, 2, and let's say 8, 3. So this is a head and this is a rest. Now, schema treats the head as an element. So now what do you think the output of this will be? So is it going to be 9, 2, 8, 3?
No, it would be 9, 8, 3.
Well, it will. This is a list. So it will treat this as a list and this as an item. Remember that the head is an item or an element, and the CDR is a list. So it looks at this as a head. Okay. So it looks at this as a head and this as a rest. But it will view, the rest is a list. You know, the rest is a list, but the head is an element. The rest is a list and the head is an element. So it will just treat this 9, 2 as an element. Okay? Why? Because it's this head, it views this head as an element. So in other words, construct here doesn't merge the two lists. It doesn't merge the two lists as you may expect it to, or concatenate the two lists. Okay. Now, let's look into write some functions that traverse lists. Now, in the first lecture on functional programming, we said that functional programming languages don't have variables and don't have loops. So if we don't have loops, what's the only way of traversing a list or doing something that requires iteration? Recursion. So everything is done through recursion. So here, I will assume that that you understand the concept of recursion and you have done recursion in C-like languages. So let's write a function for getting the last element. Define last element. Now this last element takes a list and it only takes a list. But this is the signature. So the signature is name of the function, it takes a list, and now we need to define the body of the function. Now we keep iterating. We keep iterating until we get to the end of the list, or the last element in the list. Now, remember that the way we do recursion through lists is using the CDR. The CDR gets you the rest. So you remove the head, and then CDR gets you the rest. So you keep getting the CDR. So in many functions, in many of the recursive functions using schema, you will have, somewhere you have the function that takes a certain list L, function that takes L, and somewhere you will need to do the recursion. So you apply the same function recursively to CDR L. So here, this is the list L. So basically you process the head if you need to process the head. Then you recursively apply the same function to the rest part. And this rest keeps getting smaller and smaller. The rest keeps getting smaller and smaller until it's either empty or has one element in it. And in this case, do we need the rest to get smaller until the list is empty or until the list has one element in it? Until it has one element in it. So having one element is going to be our base. Our base is one element. Now, how do we check in schema if the current list has one element in it? Well, in schema there is a null checking on a list. So it's an operator that you apply to a list. If the list is empty, this is going to return true. If the list is non-empty, it's going to return false. So given that you have a null checking, how can you check if the current list has one element in it?
You check if the rest of the list is null.
Exactly, yeah. You check the rest, which is the CDR. So you check the rest of the list. If the rest of it is empty, then we have one element in the list. So if we have one element in the list, that's what we return, right? Otherwise, what we return is going to be the recursion. So it's like, get last, or what did we call it? Last element. Of L. So if L dot size equals 1, return what? Return the element or the head of it. Return head. Else return last element of L dot get rest. Okay. So now how do we express this in schema? So first of all we check, so the if is null of the CDR of L. Now where do we need the parentheses? For CDRL, right? So the CDRL is CDRL is what we are checking for null. If this is null, then what do? We return the head of the list. We return right. So if null CDR, and no, we need parentheses for this because this is our condition. This is our then. Yes?
Do you need an equal if the equals no?
No.
No, it's just by definition here. So this does the equality. So it's this is what the semantics of this operand of this operator are checking if this list is null. So it's built in. Yeah. Otherwise, we do the recursion. So this is the else part. We return. Just we apply the same function, last element of what? So last element applied to CDRL. Last element applied to CDRL. And now we need to close the else. And then we need to close the if. And then we need to close the whole definition. Okay. Yeah, so I'm showing you what the recursion looks like in the languages that we're familiar with. Okay, so next example. Next example is checking if an element is in a list. Is in list of an element and a list. So we're given an element and a list, and the objective is to check if it's in the list. Now, writing this recursively in the languages that we're familiar with. So last element, we need to is in list. So CDR is our way of looking at the rest. So what we do is if, so here is in list, we're given X and L. If L dot get head equals X, then what? Then return true. Otherwise, search in the rest. Else, return is in list of what? Of L dot get rest of X and L dot get rest. So it's on the screen, yeah. And is this complete? What should we check for? Yeah, emptiness. If it's null, if we reach, this get rest, which is equivalent to CDR in schema, what does it do? It gets the rest. But at the end, if we reach a null list, we should return what? If L dot get size equals 0, we return false. So if get head is X, then yeah. So let's try now to write this in schema. So the first checking is null, right? So if what? Null applied to what? Applied to L. So this is the condition. If null applied to L is true, then what do we return? False. And this is false in schema. Now else it's not null. Now we compare the head. If what do we check? We compare the head with X. So if equality of, check for the equality of X and, yeah, exactly, car L, the head. So car L, check for equality with X. If it's equal, then what? What? Return true. Here, if it gets the head, if it's equal to the head, return true. Otherwise, search in the rest of the list. So rest of is CDR in schema. Else, here, the else for this is search in the rest of the list. So I'm going to call is in list, and I'm going to pass to it the same X, but my list is going to be what? Yeah, the rest of it, which is CDR L. Of course, CDR L should be between parentheses. Okay. Now I need to close everything that I have opened. So is in list of, so I need to close the else, this else. Then I need to close the if. Well, in fact, okay, so there are two ifs, and one of the ifs is the else for the other if. So this is the then, and this is the else, and the else should be between parentheses too. So these ones in blue, this is the else for the first if. So this is the then, this is the else. So I have to put this as the else for the first if. So the blue is for the blue, and this if else together is the else for the previous, for the outer if. So I close this. What else do I need to close? I still need to close this and this. Okay. Okay, so this closes the CDR, this closes this else, the inner else, then I need to close the outer else, and close this, then close this. Okay, so I hope that you now have a good idea about schema. So that